The next video in the Tools of Chemistry unit is on scientific notation. There are two learning targets for this video. The first of which, we want to express standard notation numbers in scientific notation. All scientific notation has a basic form and usage that we want to be familiar with. It is often used for very large or very small numbers. However, in the sciences and chemistry certainly, it's also very useful for sig-fig issues, because as you'll see, all non-significant figures will disappear. So we don't necessarily have to use scientific notation exclusively for really large or really small numbers. We could really use it for any number we want to if it's useful. All numbers that appear in scientific notation will have this form: some number n times 10 to the power little n, where capital N is any number between 1 and 9.9999 repeating, and we call that number the mantissa. This number out front, the big N in the equation here, is called the mantissa. The little n is simply any integer, and recall from math class, integers can be positive or negative, so any integer could be the exponent there. When we write in scientific notation, there are a few basic rules to follow. The first of which is we're going to move the decimal point, so one non-zero number is to the left of that decimal point. So here's an example. Let's say we're asked to write this number, 27,050,000, in scientific notation. The decimal point needs to be moved to the left so that there's only one non-zero digit to its left. In this case, that would be the 2. So the decimal point is going to go between the 2 and the 7. So becoming 2.7050000. However, that wouldn't be the number in scientific notation, because obviously 2.705 is very different than 27,050,000. So that's where the exponent comes in. We need to figure out which exponent of 10 to multiply by. Well, all we need to do is count the number of places we move the decimal. Starting with the decimal point to the right of that last 0 and moving it to where we did between the 2 and the 7, that's 7 places. So the exponent we're going to multiply by is 10 to the 7th. So we'll write the number with all the non-sig figs disappearing. So all these ending zeros, those are all not significant, so they disappear. So notice our answer is 2.705 times 10 to the 7th. How do we know it was 10 to the 7th? Again, we moved the decimal point 7 places. And why 7 and not negative 7? Well, consider that going from 27 million to 2.7, that number got 10 million times smaller, so we have to multiply it by 10 million in order to make those numbers the same. So here are just some examples where we're going to write numbers in scientific notation. First, 0.0046. We need to move the decimal so there's one non-zero to its left, so we're going to move it between the 4 and the 6. So it's going to go to the right 3 places, and then our answer will be 4.6 times 10 to the negative 3rd. Going to the right, the number is getting bigger, so we have to multiply by a number that's less than 1. So if we go to the right, the exponent's negative. Notice these zeros at the beginning, the leading zeros, they're not significant, so they disappear. Next, 472 million. The decimal point is going to go between the 4 and the 7. Again, one non-zero to the left of the decimal. In doing that, we move the decimal point to the left 8 spots. So 4.72 times 10 to the 8th. And all 6 of these zeros are not significant, so they disappear. Next, 0.0000580. Here the decimal point is going to go between the 5 and the 8. So we're going to move the decimal point to the right 5 places. And our answer will be 5.80 times 10 to the negative 5th. Notice here, this last 0 is significant. It's a final 0 after the decimal, so it does need to appear in the mantissa of the scientific notation. Notice here we already have a number that's written in scientific notation, or at least in a way in scientific notation, 123.45 times 10 to the 3rd. The problem here is this is not proper scientific notation because there's more than one non-zero digit to the left. So this decimal point needs to move to the left 2 places. So we'll move it between the 1 and the 2, so 1.2345. And then we moved it to the left 2 places, so the 10 to the third becomes 10 to the fifth. If we go to the left, this exponent has to get bigger because the mantissa got smaller. Similar example here. We're already in scientific notation, but the decimal point is not in a proper location. It needs to be between the 2 and the 9. So the decimal point will move to the right 1 place, and then going to the right, the exponent will get smaller. So this becomes 2.90 times 10 to the negative 8th. Recall with negative numbers, negative 8 would be smaller than negative 7. That's why it's negative 8 instead of negative 6. Same thing here. Write each number in scientific notation. I would pause the video after each number is presented and see if you can do it right before you play the video on. First one, 0.0008508. The decimal point needs to go between the 8 and the 5, so we're going to move it to the right 4 places. So that would give us 8.508 times 10 to the negative 4th. Negative because we moved the decimal to the right, so the number got bigger, so the exponent we multiply by has to be less than 1. Next one, 907. Notice here, none of these digits are not significant, so all these digits will still appear in the answer. We're going to move the decimal to the left 2 spots, so 9.07 times 10 to the second. C, 0.024 times 10 to the negative third. Here, the decimal needs to move to the right 2 places between the 2 and the 4, and that will make the exponent smaller by 2 powers, so 2.4 times 10 to the negative fifth. 28.4 times 10 to the 18th. The decimal point needs to move to the left 1 place. That will increase the exponent by 1, so 2.84 times 10 to the 19th. 0.00032 times 10 to the fourth. Exponent needs to move to the right between the 3 and the 2, so it's going to move to the right 4 places. That will make the exponent smaller by 4. So notice that would be 3.2 times 10 to the 0, or just 3.2. Anything to the 0 power is 1, so this is 3.2 times 1, or 3.2. Here's a slightly different example. We're asked to write the number 3,000 with 3, 4, and 5 significant figures without using scientific notation. The next 2 examples are really going to show you how scientific notation can make it easier to work with sig figs in some certain situations. So if we're going to write the number 3,000 with 3 sig figs, if I just write it like this, 3 with 3 zeros, that's 1 sig fig. If we're going to have 3 sig figs, that means the tens place would need to be significant. Really, about the only thing we do without scientific notation would be to put a line over that 0. And that works. Nothing wrong with that. If we're going to write it with 4 sig figs, we have a couple options. We can either put a line over that 0 in the ones place, making all of the zeros significant, or we could put a decimal point after the ones place, showing that that last 0 is estimated, meaning the other zeros are significant as well. 5 sig figs is real easy. That would be 3,000.0. That would give us 5 sig figs. Now, the same thing, we're going to write the number 3,000 with 3, 4, and 5 significant figures, but this time we're going to use scientific notation. And I think you'll see why the scientific notation makes this really easy. So the number 3,000 in scientific notation is 3 times 10 to the third. Now that would be 1 sig fig, if we were just write it like that, 3 times 10 to the third. If I wanted 3 sig figs, I just write 3.00 times 10 to the third. Still 3,000. If I want 4 sig figs, 3.000 times 10 to the third. And then 5 sig figs, I just add another 0. So you can see the scientific notation can make it very easy to deal with your significant figures in situations where you have these trailing zeros, but they're before the decimal. It can make writing those numbers with the correct number of sig figs very easy. So we've looked at how we show numbers in scientific notation. Now we want to be able to perform arithmetic, meaning add, subtract, multiply, and divide, with numbers in scientific notation. Much like our sig fig rules, we have really 2 sets of rules for doing this. One rule for adding, subtracting, and then kind of another rule for multiplying and dividing. So we'll look at the adding, subtracting first. So the rules are, if we're going to add or subtract numbers in scientific notation, the first thing we want to do is move the decimal point so that all the numbers are the same exponent. Then we'll just add the mantisses, or subtract if you're subtracting. And when you do that, remember to follow the sig fig rules. And then the exponent will stay the same. Whatever exponent we change the numbers to up here in A, they'll stay the same. And the last step is we'll check for proper scientific notation. In other words, make sure the decimal point is in the right spot. And if it's not, then you would need to move it, which would then in turn change the exponent. So let's look at an example. We're going to add 3.73 times 10 to the 18th meters to 9.02 times 10 to the 17th. Notice these two exponents are not the same. The first thing we have to do is we need to move the decimal for one of them so that the exponents are the same. Now it makes no difference which one you change. In this example, I've changed the second one to 10 to the 18th. Notice to do that, I had to move the decimal to the left one place. If the decimal goes left, then the exponent is going to get bigger. So now I'm going to add 3.73, the mantissa for the first number, to 0.902, the mantissa for the second number. And your calculator is going to tell you 4.632. But remembering your sig fig rules, we only have a sig fig to the second decimal place, or you might call it the hundredths place. It's really not the hundredths because this is 3.73 times 10 to the 18th. It would actually be way more than the hundredths place, but we can think of it that way. So I'll round it to two decimal places, in this case 4.63. The exponent then stays the same. I changed both the exponents to 10 to the 18th, so this will be 4.63 times 10 to the 18th. My last step, checking for proper scientific notation, it looks fine. The decimal's in the right spot. It's between the 4 and the 6, meaning there's only one non-zero digit to the left of the decimal. So we're good there. So the answer would be 4.63 times 10 to the 18th meters. Here's another example. This time we're subtracting, but it's still the same rules. Notice we have times 10 to the negative 13th and times 10 to the negative 15th. So this time we're going to have to move the decimal two places. In this example, I've changed the first one. Notice the decimal is moved to the right two places. So now it's 472.0. And because the decimal has moved right two places, the exponent has to get two smaller. So it's gone from negative 13 to negative 15. Now I will subtract my mantisses. So 472.0 minus 6.27. Calculator will tell you 465.73. Rounding for sig figs. Notice this first measurement only goes to the tenths place. So I'll round my answer to the tenths place, 465.7. My exponent stays the same. They're both negative 10 to the negative 15, so it'll stay there. But notice this time the decimal does not end up in the right location. I need one non-zero digit to its left, so I'll need to move the decimal two places to the left, and that will change my exponent to 10 to the negative 13th. If the decimal goes left, the exponent has to get bigger. Here are some practice problems. Again, I'd try them on your own, pause the video, see if you get them right. First in here we have some subtraction. Notice we have 10 to the 8th and 10 to the 7th. Again, it makes no difference which of the one you choose to move. Looks like in this example I've changed the second one. I've moved the decimal to the left one place. That will make the exponent get bigger, so 10 to the 7th becomes 10 to the 8th. I will now subtract the mantisses, 1.95 minus 0.277. I'll need to round my answer to two decimal places, so 1.67. And that gives us an answer of 1.67 times 10 to the 8th meters per second. Notice the scientific notation looks good here. The decimal's in the right spot, so there's nothing else to do. Next one, we have addition. 5.55 times 10 to the 55th meters cubed plus 4.44 times 10 to the 56th meters cubed. Again, makes no difference which one you change. Looks like I've changed the 55 to a 56. I've made the exponent bigger. I do that by moving the decimal to the left one place. Now I'll just add my mantisses. 0.555 plus 4.44. Calculator is going to tell you 4.995, but notice that 4.44 only goes to the hundredths place. We need to round to the hundredths place. That will round to 5.00. So that gives me 5.00 times 10 to the 56th meters cubed. One thing you might have noticed so far with this addition subtraction, if I always change my exponent to the larger value, so in the first example here I had 10 to the 8th and 10 to the 7th, if I change it to 10 to the 8th, then I probably won't have to move my decimal at the end. Same thing here, I change it to the larger one, the 10 to the 56th, as opposed to 10 to the 55th. That will usually eliminate that last step of having to correct the scientific notation to make the decimal point appear in the right place. Another example here, 3.950 times 10 to the negative 12th minus 5.432 times 10 to the negative 14th. Here I've changed it to the smaller value, actually 10 to the negative 14th, by moving the decimal to the right two places on the first measurement here. And now I'll subtract my mantisses. After rounding for sig figs, that gives me 389.6. And then leaving my exponents the same, 10 to the negative 14th, that gives me 389.6 times 10 to the negative 14th meters, which you can see I'll now have to move the decimal to the left 2 places to get it in a proper location, that leaving me with an answer of 3.896 times 10 to the negative 12th meters. So that's addition subtraction. Multiplying and dividing, I think most students find a little easier. There's a slightly different set of rules for multiplying and dividing, but they are very similar. We'll start with multiplying here. The first thing we're going to do is we're just going to multiply the mantisses. The exponents do not need to be the same when you multiply or divide. I think that's why students find this a little easier. When you multiply the mantisses, follow those sig fig rules. We will then multiply the powers of 10. And recall from algebra class, that means you're going to add the exponents. In other words, 10 to the y times 10 to the x is equal to 10 to the y plus x. You'll then simply check for proper scientific notation, and then you'd be done. So here's an example. 3.48 times 10 to the 4th centimeters times 9.03 times 10 to the 8th centimeters. The first thing we'll do is we'll just multiply the mantisses together. Your calculator is going to tell you 31.4244. Remember your sig fig rules for multiplying and dividing. We're looking at number of sig figs. Both of these measurements have 3 sig figs, so our answer has to have 3 sig figs, so that will round to 31.4. Now we'll multiply the exponents, 10 to the 4th times 10 to the 8th. Well, that would be 10 to the 12th, because 4 plus 8 is 12. So now we have an answer of 31.4 times 10 to the 12th centimeters squared. Notice our scientific notation here, the decimal is not in the right spot. Need to move it to the left 1 place. That will make my exponent bigger. So my answer is 3.14 times 10 to the 13th centimeters squared. Here's another example. 2.605 times 10 to the 23rd newtons times 7.0 times 10 to the negative 7th meters. I'll multiply the mantisses. Notice I'll just get 2 sig figs here because the 7.0 is 2 sig figs, so that will round it to 18. I will then take care of my numbers with exponents. 10 to the 23rd times 10 to the negative 7th is 10 to the 16th. 23 plus a negative 7 is 16. I'll just write my answer now. 18 times 10 to the 16th Newton meters. A Newton times a meter, so it's a Newton meter. And notice I will again need to move my decimal point to the left 1 place here. So that will make my answer 1.8 times 10 to the 17th Newton meters. Couple practice problems. Again, I would pause the video, try them yourself. So again, we have multiplication. So we'll multiply our mantisses. Just 2 sig figs because of that second measurement, so that will round to 11. I'll then need to take care of the exponents. 10 to the negative 12th times 10 to the negative 3rd. Negative 12 plus negative 3 is negative 15, so 10 to the negative 15th. That gives me 11 times 10 to the negative 15th joule seconds, which, writing in proper scientific notation, is 1.1 times 10 to the negative 14th joule seconds. Same thing here, multiplication. We're going to multiply the mantisses. Notice we will get 4 sig figs here. The first measurement has 4 sig figs. The second one's 5. So the smallest number is 4. That should round to 45.32. We'll then take care of our exponents. 10 to the 9th times 10 to the 4th is 10 to the 13th. Writing my answer, that gives me 45.32 times 10 to the 13th foot-pounds. Writing it in proper scientific notation, moving that decimal to the left 1 place, 4.532 times 10 to the 14th foot-pounds. That's multiplication. Dividing in scientific notation, very similar to multiplying. The first thing, we're just going to divide the mantisses. Like we did in multiplication, we multiplied them. We'll divide them here. Again, follow the sig fig rules. Then we'll divide the powers of 10, and recall from algebra, that means you're going to subtract the exponents. 10 to the y divided by 10 to the x is equal to 10 to the y minus x. We'll then check for proper scientific notation, and we'll be done. So here's an example. We have a division. We're going to divide the mantisses, so 4.5 divided by 1.5. Your calculator is going to tell you 3, but notice both of these measurements have 2 sig figs, so our answer needs 2 sig figs, so that will be 3.0. We'll then divide our exponents, so 10 to the 3rd divided by 10 to the 2nd. That's 10 to the 3 minus 2, which is 10 to the 1st. So our answer is 3.0 times 10 to the first meters per second. Another example, again division. We'll divide our mantisses. Notice here we'll get 2 sig figs. Both of our measurements have 2 sig figs. So plug that into your calculator and that will round to 3.7. We'll then take care of our exponents. 10 to the third divided by 10 to the fifth. So that's 10 to the 3 minus 5. That would equal 10 to the negative second. So our answer is 3.7 times 10 to the negative second grams per centimeter cubed. Another example, divide our mantisses. We have 2.2 divided by 3.3. Again, 2 sig figs is what we'll get there, so that will round to 0.67. Our exponents, this is where some students have a little difficulty. We have 10 to the fourth divided by 10 to the negative second, so we're going to subtract a negative 2. 4 minus a negative 2 would be positive 6. So my exponent will be 10 to the sixth. That gives us 0.67 times 10 to the sixth. The capital C is the unit coulomb. Coulomb per meter is what that unit would be. Notice here our scientific notation is not quite right. The decimal point needs to go to the right one place. So that will give us an answer of 6.7 times 10 to the fifth coulombs per meter. Again, some practice. Pause the video, try them yourself. First one, division here. We're going to divide the mantisses. After rounding for sig figs, that should give you 0.56, 2 sig figs there. Then we'll take care of the exponents. We have 10 to the 8th divided by 10 to the negative second. So 8 minus a negative 2 is a positive 10. So 10 to the 10th. That gives you an answer of 0.56 times 10 to the 10th kilograms per kilometer cubed. Need to move that decimal over one place. So the final answer is 5.6 times 10 to the 9th kilograms per kilometer cubed. Next one, another division. Again, we'll divide the mantisses. After rounding for sig figs, notice we have 3 sig figs here. That will give you 1.99. We'll then take care of our exponents. We have 10 to the negative fifth divided by 10 to the third. So negative 5 minus 3 is a negative 8. So 10 to the negative 8th. So our answer is 1.99 times 10 to the negative 8th centimeters. Notice your units here, centimeters squared divided by centimeters. One of those centimeters will cancel and you'll just be left with a single centimeter unit in the numerator. So we've looked at the basic operations, adding and subtracting. Remember, it's the exact same rule. You have to move the decimal so that the exponents are the same, and then you either add or subtract the mantisses and go from there. Multiplying and dividing, the exponents don't have to be the same. You simply multiply or divide the mantisses based on what the operation is, and then you take care of the exponents by either adding them or subtracting them, depending on whether it's multiplication or division.